Let's begin. Back in the early part of the century, when atom smashers were the vogue, in the early 30s, that sort of thing, 1930s and 40s, people used to try atom smashers, used to try to see if they could transmute elements from one kind to another. And one of the reactions that did succeed was kind of novel. Instead of throwing higher and higher velocity particles at matter, three people in Germany, Lisa Meitner, Otto Hahn, Otto Strassmann, I think. Anyway, what they did was they threw slow-moving neutrons at uranium isotopes, and they found a reaction that changed the world. And the reaction that changed the world is that which you see before you here. It's in your textbook. It's the first page in the chapter of fission and fusion. And all we're saying is that it turns out if a slow-moving neutron taps into uranium-235 isotope, boom, it'll lay it right in half. And the isotope, instead of a little particle coming off, like maybe a proton or an alpha particle, the whole thing falls in half. Wild. And boom, boom. Here's a typical reaction. There are many reactions. This is just a typical one. The uranium busts in half into krypton and barium. These are about halfway down the periodic table from where the uranium is. And the neat thing is there also an ejection on the average of about 3 more neutrons. Now, if you can slow these neutrons down, they're going kind of fast. If you can slow those down so they're going slow enough to cause another reaction, then you have a chain reaction. And you know what you do? You throw these neutrons into other atoms. Hey, let me ask you a physics question. If you want to throw a ball into some other balls such that the ball will slow down, would you throw the ball into an environment of heavy balls or light balls? And you want the thing to slow down. Let me ask you this. If I take a ball and I throw it against a brick wall, boom, when it bounces off, will it bounce off a lot slower or about the same? About the same. If I take a golf ball and I throw it against a bowling ball, is that bowling ball going to slow the golf ball down? No, it's not. So what you do is you take the golf ball and you throw it into an arena of ping pong balls. And if you do that, it'll give what? Give the energy to the ping pong ball, and it itself will slow down. And so what you do is you take these things and you bounce them off atoms like the size of carbon. You'd ever hear about the heavy water? You bounce them off light atoms or molecules, and these things will slow down. They say they're moderated and will cause the reaction of more of this fission. It's called nuclear fission, gang, breaking apart. Nuclear fission, and you will fission more atoms. Anyway, this is something that caused an awful lot of excitement. Because along with this, too, it turns out the kinetic energy of these particles, and these all flying apart, is awesome. The energy it takes to light up New York City, it comes about as a result of water pouring over Niagara Falls. And every water drop has an energy of about this much. 4 electron volts. Electron volts a tiny unit of energy. It's a microscopic unit of energy, yeah? But 4 electron volts per water drop. TNT? You get about 30 electron volts. A high-octane gasoline, about 30 electron volts per molecule of combustion, yeah? 1 atom, U-235, fissions, you get about 200 million electron volts of energy. Awesome, awesome. An awful lot of energy for 1 atom. And that kind of changed the world. And so we now talk about the atomic age, or more properly, the nuclear age, because we're talking about an awful lot of energy for just a little bit of matter. It turns out the most common isotope of uranium is uranium, let me try that over here, uranium-238. And when 238 catches a neutron, what it does is it turns to U-239. U-238 emits alpha particles, but 239 emits beta particles. And guess what the 239 does, gang? It turns into an element beyond uranium. We talked last time about decaying up the periodic table. What's going to be the atomic number of the element that this will decay into? What number plus a -1 going to be 92? 93. Lee. Okay. Anyone else besides Lee? How many people said it's 93? No. All right. Okay. You guys are just being a little reticent, right? Okay. It's going to be 93. And that 93 is a brand new element. It's beyond uranium, called transuranic. And that's neptunium. You know why they call it neptunium? You know what the first planet was they discovered in terms of Newton's laws? Neptune, gang. Neptune. So they call this neptunium, first element beyond uranium. And that's neptunium-239. It's got a very, very short half-life. And you know what it does? It decays. And guess what it emits? It begins with a B. No, not alpha. Try it again. Okay. It emits a beta particle. And what does it turn into? How many people can figure out what the number is here that couldn't do it before? Maybe now can. Show of hands. 4 people. Wonderful. Wonderful. Come on. Now, how many? What is it going to be, gang? 94. 94. What is the second planet that we named after discovering by Newton's laws? It wasn't Neptune. It was what? Pluto. Guess what we'd be calling this gang? Plutonium. Pu-239. And you know what plutonium will do? Plutonium, as well as uranium-235, will undergo fission when a neutron taps it. And so this is used for power production. U-235 used for power production. Historically, when the bombs were dropped back in World War II, the bomb that devastated Hiroshima was a uranium-235 bomb. Do you know how much uranium-235 was left after that bomb was detonated? Almost none. The United States shot its arsenal. 1 bomb. None left to speak of. You know what the bomb that hit Nagasaki was? Plutonium. Does the same thing. Plutonium is made from uranium-235. 238. Very plentiful. But you got to bombard it with neutrons. So you can make it. You can make plutonium. Now, why do we get this 200 million electron volts? That's what I want you to know. All you guys know that uranium splits into other elements and you get a lot of energy off, and you all know that the neutrons will cause new reactions. Nice-a-rooney. That's junior high school knowledge, yeah? Anyone takes a science course. What we want to know is why all that energy? And I have a model for you to consider, and it has to do with mass. See on the table here I have, this imagination time? Look, I have all the 92 elements in the periodic table that's found or commonly in the Earth's crust, almost all 92, are all arranged here. See the hydrogen here? See the hydrogen atom? What's this one here? Helium. What's this one? Lithium. I got no names, but you can just kind of look at them, right? What's the next one? I keep running out too. But I know what the last one is. You guys know what the last one is? 92? Begins with U. Uranium. Excellent. Okay. And so I have all the atoms all lined up here. Can you see them? At least in your mind's eye. Now what I'm going to do is I'm going to shake the atoms. I'm going to take the hydrogen, just the nucleus of the atom, okay? I take the hydrogen and I shake it back and forth, okay? Now it's harder to shake the helium. How come? Because it has more mass. There's 4 nucleons. Over here there's only 1. Then I take the lithium and I shake that. Easier or harder? What's the hardest one to shake? Why? Got more mass. Let's make a graph of how hard to shake versus atomic number. Would that be fun? That'd be a drag. But let's do it anyway, okay? Because I'm going to lead up to something that's kind of neat. How hard it is to shake. That's mass, isn't it? Mass, huh? Inertia, yeah? Versus atomic number. I'm going to start off with 1, and I go to right up here to 92. All my atoms, yeah? My graph would look something like this, gang. It'd start to go straight. It turns out the first 20 or so atoms have as many neutrons as protons, so they kind of go straight up, and then it starts to curve. And you know what this graph tells you? This graph tells you something not so wild, common sense. That if you want to take the mass, if you want to find out how massive the uranium atom is, go up here, read it over, and there's the mass. This atom here, what mass it got? You read the mass right there too, okay? This atom here, what's got the lowest mass? Hydrogen. And then they keep building up more and more massive. Nothing to it. Big deal? No, it's not a big deal. I'll show you a big deal. Let's suppose we make a graph that's similar. We make a graph of the mass per nucleon. That's different. Mass per nucleon. What's that mean? That means this. You're not going to look like that, gang. I'll tell you that. You might think it looks something like this, which is to say, how much mass does a proton have? Well, it has just as much mass here, as here, as here, as here, as here. Constant. True or false? Begins with F. False-a-rooney. False-a-rooney. Let's go back to these atoms again. Let's take the hydrogen. You shake it. Now go to hydrogen. Go to helium. and grab a nucleon. Now, just grab one nucleon and shake it. Ooh, easier. Go to lithium, grab it. Woo, easier to shake. Less mass for the protons in here than in here. And the most mass here, as we'll find out. And you keep going up, up, up the periodic table, and the nucleons are easier to shake. And you get up to iron. And it's very, very easy to get the least mass of all, because beyond iron, the nucleons seem to gain mass. And you're starting to come back up, and when you get to uranium, you still don't have as much mass as you had in hydrogen. What is going on? How massive a proton is, how massive a neutron is, apparently depends upon what configuration nucleus it's in. And that's the case. And you can kind of see that with Einstein's equivalence of mass and energy. Consider you have a nucleus. You got all these nucleons in here, right? They're all being held together, yeah? Very, very strongly. Nuclear forces, yeah? Now you want to take a nucleon. When I say nucleon, I'm talking about a proton or a neutron, yeah, gang? You take one out, and you want to grab one, and you want to pull it out of the nucleus. Easy or hard? Begin with the H. There's nuclear forces, honey. You're going to pull against that nuclear force. It's going to be hard to pull a nucleon out of there, gang. It's going to be very hard to pull out of there. You know what the hardest one to pull out is? In iron. You say to iron, iron, honey, man, you got hardly any mass in your nucleons. Iron says, try pulling me out. It's going to take an awful lot of work to pull that nucleon out of iron, more out of iron than anything else. And when you pull these nucleons out, it takes work to do that. And when you do work on that, like stretching a spring, you give it more and more what? Begin with the E. Energy. And guess how that energy is manifest? Begin with the M. Mass. And a nucleon will have more energy, which is to say, E equals mc squared, which is to say, will have more mass outside the nucleus than inside. And in there lies the secret of nuclear energy. Because a graph of the nucleons would be something like this. Put here at 92. There's the graph that really, really tells it. And it's a graph mass per nucleon versus atomic. Now, it's not the mass of the whole atom, mass of the whole nucleus. It's the mass of each nucleon in the nucleus. And you see, in hydrogen, it has the most mass of all. None of its mass is bound up with energy of binding anything else with it. It's all by itself. And as you continue to go up the periodic table, you get varying amounts of mass per nucleon. The point is, how much mass you got depends, per nucleon depends what nucleus you're in. Let's look at the uranium fission in terms of this relationship. Here's uranium right here. The uranium atom has nucleons which have about this much mass each, all right? What's going to happen to the uranium when you bust it up into krypton and barium, and those are halfway down the periodic table? That uranium nucleus is going to end up one down here and one down here. And this atom here, let's suppose it's barium. That's got less mass. Each nucleon there has less mass than you started with. You ever hear of this equation here? Rest energy equals mass times speed of light square. Okay? What happens to that mass you don't have anymore? I wonder where did it go? Energy. It's like you got uranium here, huh? You take the uranium, put it in a bathroom scale, boom, weigh 238. Now take the uranium and knock it in two pieces. Boom, boom. Now put the two pieces over here on one big bathroom scale. Less than 238. When you bust it in half, the pieces don't add up to what? See, it's not like classically thinking. If you take a loaf of bread, it weighs a pound, and you bust it in two pieces, each piece is going to be a half a pound. Or the two pieces will add up to the pound, yeah? That does not take place at the nuclear level. When you bust up one of these heavy elements, the pieces will have less mass than you started with. And that mass that's missing, multiplied by the speed of light squared, and guess what you're going to get for uranium, gang? 200 million electron volts. And there's your energy. You have converted mass, inertia, to energy. And that energy is manifest in the kinetic energy of these particles as they fly apart. That's heat. You can boil water. You can boil that water, you can turn it to steam. You can pass that steam through a nozzle, you can put a paddle wheel at the other end, you can make a paddle wheel spin. And you know what you can do with that paddle wheel? You can hook it to a generator. Then you make the generator spin. Then you know what you can do? You have some wires coming in that generator. Guess what flow through the wires? Begin with the E. Electricity. E. Only one big hassle, gang. Not only one big hassle, but one big hassle about this is when you bust the uranium up, these two pieces here are neutron rich. These are larger nuclei than their normal cousins. Okay, there's extra neutrons, makes it bigger. That's the way I look at it. The nucleus is bigger, and as you mentioned there, Paul, more unstable, and away you go. So these things are radioactive byproducts, good or bad. Well, it depends. Usually bad. What are you going to do with them? Okay, these are emitting radiations themselves. So that's a hassle, and we're all familiar with the radioactive waste problem. But you know what, gang? There's a brighter side to the whole story with nuclear power. Instead of talking about losing mass by going down, this is like an energy hill. You read that in the textbook? Think of it as an energy hill. You're rolling down the hill, you're picking up energy. That's what you're doing. You're kind of losing mass, and that mass that you're losing, so to speak, is what goes off as energy. But here we have right in the middle. What's this element right here, gang, in the very, very, very bottom? Iron. And that's atomic number 26. How about over here? How about you take an element like right about here? How about you take an element right in here? Okay, I don't know what it is. Maybe it's magnesium. And I take some magnesium and I split that too. If I split that, what will happen? Let's suppose I took an element here and I split it in two pieces. One here and one here. Would I lose mass? Or would I gain mass? Let's try it. Here I am here. After I'm through, I'm over here. I got more mass than I started with. No energy off, gang. No energy off. The name of the game for any power production, even if you're burning coal, is have less mass afterwards than you started. You get energy. If you got more mass afterwards than you started, you had to take in energy. But energy be given off if you got less mass afterwards than you begin. So on this side of the curve, on this side of iron, what do I have to do? Break apart or do what? What's the other word instead of break apart? What do I want to do? I want to fuse them, honey. I want to fuse them. I want to take these isotopes here and I want to fuse them together. Let's suppose I take some, that's what the sun and the stars do. Take some hydrogen, huh? Hydrogen, look at all the mass it's got, yeah? Now take those hydrogen, squash them together. Easy or hard to do? Very hard to do, electrical repulsion. But if you could squash them, and the sun and the stars do that, squash them together. Now it's helium. Helium got less mass per nucleon than the hydrogen had. Now don't get mixed up. Helium has almost 4 times the mass as hydrogen, but not 4 times the mass per nucleon as hydrogen. You hear what I'm saying? So it's mass per nucleon. You have to have that straight, otherwise this doesn't make sense. So you get less mass per nucleon. Hey, that mass per nucleon lost, boom. That's why the sun shines. That's why the stars shine. That's nuclear fusion. A typical reaction for hydrogen is squashing the typical fusion reaction that happens in the sun and the stars, yeah? Squash a couple of deuterium atoms together. And what you'll do is you'll get helium. Helium's what? Atomic number 2, 3. Most helium's 4, yeah? This one's 3. Where's the other one? Right here. And guess what the energy of that reaction is manifest? The kinetic energy of these, mostly this. This thing going off about the 5th the speed of light. Boom, watch out. Don't get in the way of that. That thing bump into anything going to heat them up. So you know what you can do with a reaction like this too? You can put it in water, and guess what the water will turn into? Steam. And the steam expands, right? And that expanding steam, you direct right through a nozzle. Guess what you put in the other side of the nozzle? Well, let me tell you, a paddle wheel. And the paddle wheel is going to spin, right? And guess what you hook the paddle wheel to? A generator. Very good. The generator. And the generator is going to generate what? Yeah, you get electricity. So you can get electricity from either fission power or fusion power. And there's the fusing of elements, huh? Another reaction is this. Tritium. Tritium, that's the heaviest isotope of hydrogen. And that goes to good old helium-4 plus a neutron. This is stuff that you see in the kids' balloons, yeah? Okay. Those reactions, a lot of energy. Not so much energy per reaction as this, but you have a lot more of those in a gram of matter than you do this. So gram for gram, you'll get more energy from nuclear fusion of little isotopes down in here than you will nuclear fission of heavy isotopes over here. The name of the game is, on this graph, gang, is to get a reaction that goes toward iron. If you're heavier than iron, you want something that after you're through, your products are closer toward iron. See, because you'll be losing mass. The name of the game, lose mass. On this side of iron, to go toward iron, you got to go this way. So what you do is you combine atomic numbers. You take things and you squash them together. As they squash together, they lose mass. That mass that's lost, they call it mass defects, not really lost. Okay? That mass then is the energy of your reaction. And it really, really works out neat. If you understand all this, if you do, you can answer this question. We said before, the uranium will bust into krypton and barium. And when it does that, 200 million electron volts is the energy of the reactants, yeah? Let's suppose instead you took some krypton and you took some barium, a couple of nuclei, and you tried to squash them together. It would be very difficult. You know why? Because you've got all these protons repelling. It would be very, very difficult. But let's suppose you did do that and you fused them together and snap. How much energy would it take to fuse them together so they snap? How many say, I got no idea, this is nuclear physics, honey, I'm not into nukes? How many say, well, when they flew apart, if they get 200 million electron volts, maybe nature's symmetric, maybe it would take 200 million electron volts to put them back together again. That's it, you get it right back together. Because when you take these two things and slam them together, they'll have more mass afterwards. How much more? That much more mass. And how much does that convert to energy-wise? 200 million electron volts. So you see, when you try to fission things, when you try to fuse things on this side, if you fuse these things, you're going to climb the hill. You're going to gain mass. What you want to do is lose mass after the reaction. Lose mass. If you understand that, you can answer this question. Let's suppose you have some iron. And with this iron, it's in the future. We get fusion power plants, we get fission power plants. And in the future, we have these, and you get some iron. You want to bring the iron to the power plant so you can get some energy out of it. Should you bring the iron to the fission power plant or the fusion power plant? Check your neighbor. See if your neighbor be knowing. Okay, gang, what would be the answer? What happened if you fission it? Iron 6. Let's suppose you fissioned it exactly in half. Then the two pieces would have what atomic number? You'd have to know what half of 26 is. What is it, 13? Is it 13? Okay, it'd be two 13s, yeah? With the two 13, you'd have more mass afterwards. You ain't going to get off, you're not going to get more mass and get more energy. Come on, take your pick. So that won't work. Let's suppose we take a couple of iron atoms and we fuse them. Fuse them. Whip. Now it's going to be what? You'd have to know what 26 times 2 is. Well, you got friends that can tell you, yeah? Okay. You see, 52. We can do it ourselves. Hey, we can do these things ourselves, all right? Okay, so it'd be 52. 52's way up here. You'd have more. Iron, honey, is the atomic sink, the nuclear sink. You'll get no energy out of iron. And when you start fusing atoms beyond iron, you end up with energy being absorbed. When you take your astronomy course, you're going to learn about how all the elements are made. They're made by hydrogen atom being squashed, fused right up to periodic table. When you get up to iron, they start squashing them together. Your star stops growing. Your star starts to cool down. Because when you start to fuse heavy elements like this, energy is required, not liberated. And your star then cools. All these elements here are made in catastrophic reactions when stars blow up, supernova. These elements are a lot more rare than these elements down here. It's just simple fusion in the sun and stars doing these. Beyond there, it takes different reactions altogether. Neat how it figured this all out, at least to this level. Now, what haven't we figured out yet? It keeps going. Beautiful. Now, it turns out the sun is burning, converting matter to energy every second. Every second go by, 4.5 billion tons of matter are not there anymore. That's sunshine. 4.5 billion tons. Every time if you look at the sun today, you know it's a little bit smaller than yesterday. 4.5 billion tons per second being sent off as radiation. Light, yeah? Now, that sounds scary, but the sun is what? Beginning with a B. And with G. Got an I in the middle. It is big, honey. It is a big, big sun. So big that at that rate, at the end of 1 million years, only 1/10,000,000th of its mass is gone. So it's a very big sun, even bigger than us, bigger in this room I mean, bigger than the whole building. You know what I'm saying? It's a big, come on, I'm kidding. It's an enormous sun. Okay. But that's what the sun is doing. The sun is converting that to power. Why don't we do that here on Earth? Why don't we take what the sun and the stars do and just do it in here on Earth and have fusion power? We got a lot of fission power plants. How about fusion power plants? Do you know how many fusion power plants there are in the world today? This is the 1990s almost, yeah? About the 1990s. How many fusion power plants in the world? Begin with a Z, honey. Yeah, 0. No fusion power plants. HC. Well, a century ago, there were no airplanes. People say, how come there's no airplanes? The birds do it. Why don't we have airplanes? What do we have to get our feet wet for when we go from one continent to another? Why don't you get in a great big airplane and go out in the sky? What would people say 100 years ago? Our time will come. Our time will come, but not yet. And now we say, why don't we have fusion power plants? You don't have any radioactive waste? This is a dream come true. You know, you get more energy out of 10 liters per water per second than you get out of all the power plants in North America, counting Canada. 10 liters of water per second? I mean, the poorest nation in the world can muster up 10 liters of water per second. That's seawater, any kind of water. If you could fuse the hydrogen in there, you talk about big energy, gang. Enormous energy. You're going to dwarf all this stuff about oil and whale oil. I mean, already we've forgotten about whale oil, right? When you guys, you grew up burning whale oil? No, you used petroleum, right? What did your great-grandfathers do? Whale oil. The world's changing. And when we get up to where we can harness this kind of thing, different. Because the fuel is the most abundant element in the universe. Hydrogen. Over 90% of the universe estimated to be hydrogen. The universe, gang, as far as the human condition, does it seem designed for where we are now, where we've been, or where we're going? It's all fusion fuel out there, gang. Now, we haven't been able to do that now because it's very difficult to do. It was difficult to make airplanes fly at first, too. Interestingly enough, you know the hang glider? The hang glider. Do you know when you guys are too young to know about this, but the hang glider was developed after human beings got to the moon. I mean, that one kind of funny. Yeah, the hang glider was developed by techniques at NASA, working on moon projects, and after the human being got to the moon in 1969, then the advent of the hang glider came out. Now that's upside down. Wouldn't you have predicted that differently if you were a futurist 100 years ago? You know, just a kite, man. Just get a kite and big enough. Come less. So sometimes the succession doesn't always go as you would expect.
Just before.
Say again?
Just before.
Oh, hang glider just before?
Yeah, because it was designed to bring back the Gemini, and they said it wouldn't work, but somebody said, well, hey, what about a person? So
How soon before, Paul?
about 3 years.
Well, but let me correct that. You know, gang, the hang glider.
Thanks, Paul.
You know, Paul Casey's a science writer. Do you know that he's taken our class? He makes his living writing science articles. Yeah. Anyway, the name of the game is this game. We have to be patient with where we are in our history. I mean, everything doesn't happen at once. We're still growing, you know. Now, with this fusion, how come we don't have fusion power plants? It's too hard to take these things and push them together. It's enormous electrical repulsion. If you heat this stuff up to a gas, maybe above 100 million degrees, these things will be going fast enough they'll scrunch. How does the sun and the stars do it? Brute force. Gravity. I said, I don't care the electrical repulsion, no electrical repulsion. Wham, right in. And the sun and the stars just brute force these things together, and this you get your fusion. Now, how do we get that? How do we do that on Earth? We've been trying brute force with plasma reactors. Heat these things up to over 100 million degrees, get that gas, pinch it with magnetic fields, boom, try to get it to fuse. Has the human race done that? Yes, we've done that. Have we had a sustained reaction? No, we haven't had a sustained reaction. Have we had any reaction to give off more energy and put in? No, we haven't. How come? Our time has not yet come. We're trying different techniques. We're trying out with lasers. What we do is take little pellets, drop them. You read this in the textbook. Little pellets of hydrogen. Take all these lasers, wham, brute force, smash these things together. And that's worked too. Sustained reaction, more energy out than required to operate the lasers. Begin with an N. No. Why? It's not our time. Kind of loose way of putting it. And there's another way too. They've done it all together without brute force. And I'm talking about cold fusion. I'm not talking about the Utah experiments that caused all this publicity in 1989. I'm talking about 1988, was it? 1988, 1989, yeah. I'm not talking about those reactions, which of course were sort of a more publicity stunt than anything else. I'm talking about the cold fusion that's muon induced. See, here's a problem with that. Let's get into that just a little bit. Let's suppose I get this proton over here, and I want this proton to fuse into that. Well, once I get beyond the electron here, it's going to be an enormous repulsion. Very, very tough to do, okay? Because this positive charges repel. But what if this electron were replaced by another particle that behaved like an electron, but was much, much more massive and would orbit way down in here? There is such a particle, and it's called a mu meson. And a mu meson has the same charge of an electron, and it will orbit very, very close. Now, when this proton is coming over to here, is it repelled by this configuration? No, it is not, because it sees a neutral charge. It's very, very close. And what happens, and they've succeeded in doing this, spitting mu mesons into this hydrogen gas, and it will take the place of the electron, and this thing will come right over, and boom, snap, fuses at room temperature almost. And this is really, really neat. Only one trouble, only one trouble. The mu mesons are very, very short-lived. They only last 2 millionths of a second. But you know what? They can get, it turns out when this thing reacts, it fires the mu meson back, and that can hit another one. And another. They had more than 100 times in its lifetime a mu meson could make a reaction. This is very, very exciting. This is cold fusion. And they do it, it works best at about 900 degrees Fahrenheit. Very, very cool compared to anything else. So read about this in the text and watch for it. It's kind of like a contender. There are problems because these mu mesons are hard to come by. It takes energy to get those. And so far, we can't see a way that we can get more energy out of the reaction than it takes to fire it up to begin with. So these are problems that the technician types are working on now, the physics types and the technology types are working on. But when and if and when they're solved, things are going to be like different, really different. Questions?
I didn't quite catch the deal on breeder reactors because you say losing mass is the name of the game. Breeder reactors make it.
Let's go through that very, very quickly. Breeder reactor. What a breeder reactor does is very simple. If in your reactor you have 238 of plutonium, a 235 in plutonium with it causing the fissioning, if you put in some U-238, I erased it over here, the 238 will be turned to plutonium. So you're really not gaining any mass. What you're doing is you're converting something that's not very helpful, 238, you're converting that to something that is very helpful energy-wise, plutonium. And the analogy I use in the book, it's like putting some water in your gasoline in your car. So it isn't like you get more mass than you started with. You're just converting the water to the gasoline. Or in this case, you're converting the 238 to plutonium. And when it turns out every reactor is all the time breeding. If you have any 238 in there at all, it's going to turn to plutonium. Some of it's going to do that. So all fission reactors are, to some extent, breeder reactors. It's just whether or not you design your reactor so that's a main feature or not.
But if we chose to make a reactor with plutonium, wouldn't that be all too unstable? Or that's what I remember from my reading is that there's always a chance that a plutonium reactor might explode. So that's somewhat impossible.
Yeah, to my knowledge, that's not the danger. No more dangerous with the plutonium than 235. It's not a question of exploding. If the Chernobyl reactor didn't explode, it overheated. To cause these things to explode, to make a bomb, you have to have stuff contained. You have to have it contained and crushed together. And reactors won't explode. It won't blow up like a bomb. You wouldn't see like a Hiroshima or a big cloud. No reactor will do that. What they'll do is they'll overheat. They'll overheat and melt down. And all this stuff all spew out and it gets in the environment. Is that good or bad? Begin with a B. Yeah, but it's not an explosion. Yeah. Now this thing over here, this is not even, you can't, this is at low temperatures and it's sort of self-sustaining. This has no chance at all of being used for a weapon, which is kind of, this is all in the textbook. Kind of read about all that. The neat thing is if we get to the point where we have like a fusion age, then all this idea of getting oil and things like that for fuel, we have no more problem with energy. And how do we make matter? Matter is made by what? Fusing things together. I think the day will come when human beings will do that. What's the world going to be like when there's abundant energy and abundant materials, no more scarcities? It's going to be different. Now, is that going to be good or be bad? It's hard to say. But I think of one thing. I think of my own story when I was a kid. I remember I knew what I wanted to do. A lot of kids don't know what they want to do when they grow up. I knew what I wanted to do. I had it all straight, man. I was going to be an airplane pilot. Because I lived near Muller Field, and I look out Muller Field, see those guys there riding these little airplanes up, and they put the caps on and the glasses and everything, put the cigarettes right up in the hair, okay, remember that? And they fly up there, man, they can see, we climb the trees and kind of look out, you know, you kind of see far, but these guys up above going by in these airplanes, that's where it's at. I knew I was going to be an airplane pilot. But I had a hang-up, like most kids do. And my hang-up is that I didn't know how to tie my shoes. And my sister used to humiliate me because I couldn't tie my shoes, and she could, and she was younger than me. And I was afraid when I got to be an airplane pilot that my sister was going to tell on me. And all those people would humiliate me, and I would be humiliated. And I really had a problem about that. How am I going to fly these? I'll have to get the kind of shoes that you don't have to tie, you know? And I was really, as a kid, worried about that. And I think in a similar way, we kind of worry about what the future's going to be, too. Not realizing by the time the future comes, honey, we'll be able to tie our shoes. We'll tie our shoes and do better than that. So when that future comes, we'll be ready for it. But a lot of changes, gang. Think about these things.